Okay. And so what are the forces on each wire due to the magnetic field produced by the other? And so the first question I would ask is, so let's say we're going to figure out what the force is on the top wire, right, due to the magnetic field produced by the bottom wire. And so the first question is, well, what is the magnetic field produced by the bottom wire at the position where the top wire is? These, I think, are a distance r apart, right? And so what rule would we use to figure out what the magnetic field, what say the direction is of the magnetic field due to this wire up by this wire?
Is that the second right-hand rule?
Yes, ma'am. That's right. And the second right-hand rule says, you grab the wire with your thumb in the direction of the current. And so your fingers will curl around the wire in the direction of the magnetic field. And so I just have a piece of wire here in the lab. And so, if that's my wire, right? If I grab the wire, or my wire, so here's my wire, I grab the wire. So above the wire, I'm going into the board. And so I would say at the position of this wire, the magnetic field due to this wire is into the board because I'd be grabbing like this. Above the wire, I'd be going in. And so I would call this B prime is into the board near the top wire, right? Can anybody tell me what the formula is for the magnetic field due to a wire at a distance from the wire? Do you remember that formula? Should be on your equation sheet if you have one handy.
The mu I prime over 2 pi r, or just I.
Yeah, that's exactly right. And so that's the magnetic field produced up here by this wire and by the bottom wire. And so this is the magnetic field that produces a force on this guy. And so now we know what the magnetic field is and the current. How do we get the force on this wire if we know the current of the wire and the magnetic field it's living in? What's the formula for that one? It's for the force on a wire in a magnetic field. It would be F equals. Also on your equation sheet.
ILB sine theta.
Yeah. And so this is ILB sine theta. And so what is the theta between? What's that angle between? It's between what and what? All of my questions are. Yeah, go ahead.
The current and the magnetic field.
Exactly right. So the magnetic field's going this way, the current's going in. So what's the angle?
90.
Yeah, and so this is just 1 because sine of 90 is 1. And this should be a B prime. And really, if I was being specific, I would say force due to I prime on I might write it like that during class, is equal to IL B prime. And so it's equal to IL times, and then I would put in mu naught I prime over 2 pi r. And so then I would say it's equal to mu naught I prime over 2 pi r. That's what the force due to I on I prime is. The magnetic field produced by this guy reaches out and has a force on this guy. And that's the value of the force. So what's the direction of the force? Can anybody tell me that? So this equation has a different right-hand rule than this equation, right? How do we get the direction for a force on a wire due to a magnetic field it's living in? Excuse me. So that's the first right-hand rule. I'm going to turn the board here just a little bit, so I don't have to get up and walk. But it's where you run your arm down the direction of the wire and you curl your fingers towards the magnetic field. And so if you want to know the force on a moving charge or a current, lay your arm out in the direction of the current, curl your fingers. So I'm curling them into the board because that's the direction of B. And then my thumb points out. And so that's the direction of the force. The only exception to that is if the moving charges were negative, but in this case, we ignore that. That's just for if you have a V here and it's the velocity and you have a QVB instead of an ILB. So I have this force F I prime on I. So can anybody tell me just by looking at what's on the board, what the force is due to this guy, the magnetic field from this guy on this guy, magnitude and direction? You can answer the question in just a couple of words. Think of Newton's third law. If you remember that one. Okay. It's equal and opposite. Right. Whatever force this guy exerts on this guy exerts back on this guy. So it'd be the same magnitude and it would be in the opposite direction. But let's go ahead and calculate it anyway, right? Just like we did for this guy. We'll first calculate the magnetic field due to this guy where this guy lives, right? And so somebody tell me, what's the direction of the magnetic field due to this guy down here? Can you do a second right-hand rule for that and figure that out?
Would it also be going down?
It would, because I want to try to grab it with my thumb in the direction of the current, but I can't. So I'm going to turn the board again, right? And I'm going to say, look, if I grab the wire with my thumb pointing in the direction I picked for the current, then my fingers are going into the board down here. If the current had been going the other way, then my fingers would be coming out of the board to get my thumb pointed in the right direction. So they're going this way, so they're going into the board. And that means that I'll call it B, right? B also goes in. I must have picked up a different marker, right? So what's the formula for B? If this is the formula for B due to this guy, what's the formula for B due to this guy?
Mu I over 2 pi r?
Yeah. Am I still on screen? Yeah, kind of. All right, good. And so what's the direction of the force for this guy? So now I've got a magnetic field going into the board, and I've got a current going this way. What's the direction for the force?
Is it down?
Yeah. Once again, I have to push my fingers along the direction of the current, push my arm along the direction of the current, curl my fingers towards the direction of the magnetic field, and my thumb points in the direction of the current. And I mean the direction of the force. F equals I, L, B. In this case, it's I prime. And I might want to call this F prime. I don't know, but this is F, sorry. This is F, I on I prime. And it's equal to I prime times L times B, which is I prime times L times mu naught I over 2 pi r. And you can see that this formula is exactly the same as this formula. Right.
On the top formula that you circled, should there be an L in it too?
Oh, there should. I lost my L. Thank you. Yes. L is the length, and I just made up this problem, and so I didn't really give it a length, but I just assumed it. Sometimes in a problem like this, they'll ask you for the force per length, and so you're calculating F over L, and then you get this thing without the L again. So. Does this board work okay?
Yes.
All right. Does that answer your question on that one?
Yeah, that helps.
All right. What's next?
On resistors, when is it that the current, I'm getting confused on when the current is the same when there's multiple resistors.
Okay.
Is it when they're in is it parallel or series? I can't remember that.
So I always try to think of these as plumbing. I think for the flow, it works for that. For the current, so the current just batteries don't produce current. They just pump the way a water pump pumps. The water pump doesn't produce water. It just moves water from somewhere behind it to somewhere in front of it. And so it's constantly just grabbing water and pushing water through. sometimes energizing it, raising it up really high, or getting it going really fast or something. That's exactly what batteries do. They're not like storing current. They're just pumps for pumping current. And so any charge, that's why when you cut a wire like that, when you break a circuit, charge can't flow because there's no place for the battery to get charged from. And so, or even worse, if you short circuit something so that there's no drag, there's no resistance, then it can pump like a battery can pump like a huge current. And that's how you get a short and a fire and stuff like that, produces a fire and stuff because everything gets really hot. But if your circuit's set up right, then a series circuit means everybody gets the same current because the charges have no choice but to run through everything on the circuit. And so maybe I should write it this way. Resistors in series all get the same current, whereas resistors in parallel right? Some of the, whatever is leaving the battery is coming back in. So if I want to call this like I1, or just call it I, then if I is leaving, I is what has to come back in through the battery. This is R1, and I might call this I1. This is R2. I'm going to put it on the side, R2. I2. And so all I know is that I equals I1 plus I2, because whatever leaves the battery gets split up between these two. I2 runs all the way around here and all the way around to here, right? That's I2. I1 runs from here to here. Right? Am I on the board still? Maybe not. And then I is what happens when these two guys merge. Have I answered your question?
Yeah, so like when resistors are in series, they have the same current.
Yeah.
But when they're in parallel, they don't.
That's right. That's right.
And then the ones in parallel, they have the same. Do they have the same voltage?
Yeah. So the voltage argument is sort of based on the same kind of idea. I'll just erase this one since I made such a mess out of it. Right. And I'll draw another one. This is my battery. You can see R1 and R2, right? There's a wire connecting the one end of R1 to one end of the battery and the other end of R1 to the other end of the battery. That's all that needs to happen to R1 for it to know that it has the full voltage of the battery across it. R2 is the same thing. There's a wire going from R2 to the top of the battery and the other end of R2 to the bottom of the battery. And so that's how I know if this is 12 volts, there's 12 volts across R1, and there's 12 volts across R2. That does not work in a series circuit. This end of the battery is not connected to the other end of R1. One end of the battery is connected to one end of R1, but the other end is not connected here. So I cannot say I have, if this is 12 volts, I do not have 12 volts across this battery. I only have something less than that because part of the voltage is used up across here. Whereas in parallel, they all have the same voltage. Where it gets complicated. So I'm sorry, go ahead.
For when they're in a series, the voltage is like, if you gave a voltage of like 12, with that 12 volts, that would just be for like the whole thing, but yes. Each one would have 6 and
8 and 4 maybe, or 6 and 6, or 3 and 9.
Okay.
So That's awesome. Sorry. So I can let me just do an example of that. Just a simple example so we can talk about it. I'll just pick the series one first, and we'll pick like, I don't know, we'll pick, we'll say V is 12 volts and R1 is, let's pick something that's easy to work with, like, I don't know, 3 ohms and 6 ohms or something like that, right? And so these are in series, and so we know that the series formula, R series, is just equal to R1 plus R2, right? And that came from, I can just sort of derive that for you quickly. This is V, right? I can say, look, if I just imagine this whole circuit, suppose somebody put these 2 resistors in a little blue box and I couldn't see inside the box. So I knew there was resistance in there, but I didn't know that it was 2 resistors in series. I'm just naming it R series. I don't know what's inside the box. Well, I know that by Ohm's law, V is equal to I times R series. And so I can figure out what, if I know the resistance and I know the voltage, I can figure out the current, right? I can say the current is equal to V over R series, something like that. But this is Ohm's law. Ohm's law applies to the resistors as well. I can say, look, V1 is equal to I1 R1, and V2, sorry, I times R1, we can call it I1 if we wanted to. V2 is equal to I times R2, where this is the current through R1, and this is the current through R2, but they're all the same because everybody gets the same current. Right? And so these voltages, the total voltage in a circuit has to add up to the total voltage on the battery. And so V1 plus V2 is equal to V. But what that means is I times R1 plus I times R2 is equal to I times R series. But we already said everybody has the same current. And so R1 plus R2 equals R series for a parallel circuit. And so I could just do this calculation for this. I could say, well, look, R series is equal to R1 plus R2. That's equal to 3 ohms plus 6 ohms. That's equal to 9 ohms. That's my series resistance. And so the current is equal to V over R series, which is 12 volts over 9 ohms. I gotta erase some of this stuff. Which is 1.33 amps, right? And that means V1 is equal to 1.33 amps times 3 ohms, which is 4 volts. And V2 is also equal to 1.33 amps, but this times 6 ohms, which is 8 volts. And then 4 plus 8 is 12. Does that work? Did I say too much?
No, that helped.
Let's do a parallel one real fast. The one we're looking at. So I'm going to pick 12 volts again. I just want to make sure I don't pick numbers that I can't do fractions with. So I'm going to pick R1 is 3 ohms, and I'll pick R2 is 6 ohms. Right. And then we could say, well, first of all, we could sort of figure out everything by hand here. If this is, like we said a minute ago, this is I1 going through here, and this is I2 going through here, right? And so we could say, since we know that the voltage across this guy is the same thing as the voltage on the battery, for reasons we just talked about, we could use Ohm's law and say I1 R1 is equal to V, or I1 is equal to V over R1. That's 12 volts over 3 ohms, which is 4 amps. Similarly, we could say I2 is equal to the same voltage over R2, which is 12 volts over 6 ohms, which is 2 amps. And then we could say, so this is I2, and this is I1, sorry, that's I1. And so this is, this guy here and this guy here, we just call them I equals I1 plus I2. It's the sum of these two currents, right? Because this is what gets split up to make these two guys, right? I2 goes that way. Or when they come back on the other side, they recombine like two rivers, right? And so I is equal to I1 plus I2, which is 6 amps. And we could have also said, look, by the argument I made just a minute ago, I could say, look, here's a box. I don't know what's inside it. There's some resistors inside it. I'm going to call it RP for R parallel, but because I do know what's inside it, but let's pretend I don't. We just gave it the name RP, right? Then we could say, look, I total, the total current, the I, is just equal to the voltage over whatever that total resistance is, R parallel, right? But we know this is equal to I1 plus I2 because it's just the sum of these two currents. And so that means V over R parallel is equal to V over R1 plus V over R2, because that's what I1 and I2 are. I1 is V over R1, I2 is V over R2. Well, the voltage is the same on everybody, and so that just says 1 over R parallel is equal to 1 over R1 plus 1 over R2, right? And so that's our parallel resistance formula. And if we add those up, we get 1 over 3 ohms plus 1 over 6 ohms, right? And that's equal to 1 over 2 ohms, which says that, sorry, I'm messing this up, but it says that R parallel is equal to 2 ohms, right? Because a third and a sixth is a half. And I flip that to get R parallel, and that's 2 ohms. And then I can calculate V over R parallel, which is 12 volts over 2 ohms, which is 6 amps, which is what I calculated the other way. I get the same answer, right? 12 volts divided by this total resistance, R parallel, gives me the 6 amps again. How do you calculate the power in a resistor, the power that's being consumed? Do you see that formula on your sheet anywhere?
Is it I squared R?
Yeah, so there's several ways to write it. But if I know the current and the resistance for a resistor, I can write the power as I squared R. Since I times R is V, I could also write that as I times V, right? Because V is just I times R, and so I squared R just gives me IV. Furthermore, the current is V over R, so I can also write it as V squared over R. So I squared R, IV, and V squared over R are all the same thing, just rearranged using Ohm's law. So could you calculate, I got that off, did I get that off screen? Could you calculate the current through each resistor, the voltage across each resistor, and the power through each resistor? So suppose I just asked you what the total resistance was. How would you calculate that?
You would have to add R2 and R3 in parallel, and then add that with R1 like it's in series.
Yeah, everybody get that? So what is it? What do I get when I add R2 and R3 in parallel?
That's the one we just did.
Yes, it is.
So 2.
Yeah, so I'd say, so if I wanted to call this R parallel, 1 over R parallel is equal to 1 over R2 plus 1 over R3. That's equal to 1 over 3 ohms plus 1 over 6 ohms. So 1 over 2 ohms. And so R parallel is 2 ohms. And so then how do I calculate the series resistance?
It'd just be 2 plus 2.
Yeah. And so R series is equal to R1 plus R2. R parallel, sorry. R1 plus R parallel, which is 2 ohms plus 2 ohms. Don't ask me why they used an R2, a 3 ohm and a 6 ohm resistor in parallel to make a 2 ohm resistor. Maybe they didn't have another 2 ohm resistor. That's a different question, I guess. So that's 4 ohms, right? And so that's the total resistance of my circuit. So what's the total current?
And 12 over 4.
Yes, it would. And so I is equal to V over R series, which is 12 volts, or 4 ohms, which is 3 amps. Assuming I did all that right. So now tell me, what's the voltage across R1? What's the current through R1?
3.
Yes, it is. This says the battery's pumping out 3 amps. That current has no choice but to go through R1. When it leaves the battery, it has no choice but to go through here. And so V1 is just equal to I times R1, which is 3 amps times 2 ohms, which is 6 volts. And so that means there's 6 volts across R1, right? What's the voltage across the parallel resistors?
It would have to be 6, right?
It would. I've got 12 volts on the battery. I've used 6 of it here. Volts is just energy per charge. I started my B's out with 6 joules per coulomb. I just call them B's. I imagine the little charges as B's that have a certain amount of energy, right? I use 6 joules per coulomb here, and so there's 6 joules per coulomb of charge left. And so that's what's across these guys. And so now I know the voltage across each one of these guys, right? So how would I get the current in R2?
It would be 6 volts over 3 ohms.
Yay. So it's the voltage across here, which is 6 volts. I'll call it V2, even though it's also V3. Maybe I'll say V2 equals V3 equals 6 volts, right? And so V2 is 6 volts. And so I2 is V2 over R2. I'm going to mess out of that, which is 6 volts over 3 ohms. And so I2 equals 2 amps. Can anybody tell me, without doing a calculation now, what's the current through R3? Or just do a really simple calculation.
1.
You got the right idea, I think. What's the current through R1? What's the current through this guy?
3.
What's the current through this guy? Oh, you said it. It's 1, you're right.
Oh, okay.
I'll pretend I meant to do that. For some reason, I had this one in my head as 6. Yeah, it's 1, right? It's 3 amps here, and 2 of them went this way, so 1 was left to go that way. That's perfect. All right. And so, but we can calculate it too if we wanted to. We have 6 volts divided by 6 ohms is 1 amp. Right. And so sometimes you can just, you can just look at the difference between the two currents and see how much is going there. The other way is to just divide the two numbers. This one was easy either way, I guess. So what's the power on R3? What power does R3 consume? Yep.
Is it 6?
I'm not going to argue with you this time. Yeah, it's 6, right? Because it's V3 I3, which is 6 volts times 3 amps. And if you remember, a volt is a joule per coulomb, and an amp is a coulomb per second. And so the coulombs cancel, and you get, what did I say, 1? Sorry, I3 is 1. And so it's equal to 6 joules per second, which is a watt. Voltage is energy per charge, coulomb is charges per second. And so when you multiply the two together, you get how much energy per second is going through that resistor. And so that's the power it's consuming. Those were all good questions.
Can I just ask a question from the book?
Yeah, come on, you bet.
It says a 500 ohm resistor is connected in series with a capacitor. What must the capacitance of the capacitor, or what must be the capacitance of the capacitor to produce a time constant of 2 seconds?
The time constant is just R times C.
Okay.
And so they're telling you this is 2 seconds. I forget what number you gave me for this, but C is equal to the time constant divided by R.
Okay, it was 500 ohms in 2 seconds.
Okay, so it's 2 seconds over 500 ohms, which is, what is that? 4 times 5, was it 500 ohms or 500 kilo ohms?
It just says ohms.
Okay.
It's very old.
And so it's, is that 0.004
Yes.
farads?
Thank you.
Oh, you bet. You know, did we do this lab? I don't think we did this lab. What was the last lab we did? Was it the,
Was it the light bulb one?
oh, yeah, we didn't get to it.
It might not have been the light bulb one, but that's the last one I remember, I think.
I was thinking it was the one with the charge to mass ratio one. Is that? Wow, it's been so long, I can't even remember. Let me just go look. I'm in the lab room right now. I might as well look. Yeah, it's charge to mass ratio. Yeah, so we would have done a lab on this. But capacitors charge up, and so a big resistor means it takes a long time for the voltage to charge up that capacitor for charge to run onto it. That's the idea. So if you have a big resistor or a big capacitor, you have a large time constant. The time constant is like the time it measures to charge up. I had a job in a physics lab, like in a research lab when I was an undergraduate. And they had it was a high energy physics lab, and they had these capacitors that were 100,000 volts a piece. And they had like 50 of them because they were making like 5 million volt particle accelerator thing or something. And we had to take them out. We were just, so I was just like unscrewing stuff. That was what most of my job was in that lab. And they had been charged up the night before or something. And I put my hand across one of them, and it shocked the heck out of me. And the guy said, he was over a loudspeaker. He was in a different room. He was telling me what to do. And he said, oh, the discharging resistor, this thing must have been too high. Why don't you come back in an hour and try it again? And I felt like it probably wasn't that bad, but I felt like it had nearly killed me. So I told him I would do it right after he did one. And he said, we'll do it next week. So anyway, that's charging and discharging a capacitor. The time it takes to charge them, it's just the product of the resistance and the capacitance. If it's either a big capacitor, it takes a long time, or if it's either a big resistor, it takes a long time, or both. And that's what our lab was going to show. Any other questions? All right. Should we meet tomorrow at 7:30?
Yes.
All right. You guys have a good night.
You too. Thank you.
Thank you. Thanks for coming, everybody, or attending, whatever that means.